got Born-Haber cycle problem. We've got to calculate the enthalpy of formation of potassium chloride given that the lattice enthalpy of formation of potassium chloride is minus 710 kilojoules per mole. So let's have a go at doing our Born-Haber cycle first. So I'll just draw a few lines on here. Okay, so for potassium chloride, it's given us the lattice enthalpy of formation of potassium chloride. So that is the formation of potassium chloride, ionic compound, from its ions in their gaseous state. So the ions of potassium chloride are K plus and Cl minus. And that's the lattice enthalpy. And that's minus 710 kilojoules per mole. And then, so we've got to get from the ionic compound to the gaseous ions. And the first step of that is to do the enthalpy of formation, which is the formation of the ionic compound from its elements in their standard states under standard conditions. So we've got potassium, which is a solid, and chlorine, which is Cl2, gaseous molecule, and then to balance, we would need a half Cl2 there.
Of course.
And then that's our enthalpy of formation, and that's what we're trying to calculate. So here we've got the elements, and the stages we go through is we go from the elements, then we'll go to the atoms, and then we'll end up at the gaseous ions over here. So first we'll get the gaseous atom of potassium. That's the enthalpy of atomization of potassium. And that, if we look at the table, is plus 90 kilojoules per mole. So we've still got our chlorine. And then we need to turn the chlorine molecule into a gaseous atom. And that's, if we look at the table, atomization of chlorine is plus 121. Then we need to turn the gaseous atoms into ions. So we'll start with the metal. Potassium's in group 1, so it goes to a positive 1 ion. And that removes an electron. And we've still got the chlorine gas. So that's the ionization energy. First ionization enthalpy of potassium. And from the table, you can see that's 418. And then the last enthalpy change here is Cl to Cl minus, and that's called electron affinity. And for chlorine, first electron affinity, minus 364. And then to work out the enthalpy of formation, if we notice the enthalpy of formation arrow is going anti-clockwise, all the other arrows are going clockwise. So that equals that. And so we can say that the enthalpy of formation is equal to all the other enthalpy changes, which in this case would be 90 plus 121 plus 418 plus minus 364 and then plus minus 710 kilojoules per mole, and then just putting those into the calculator would give us the enthalpy of formation of potassium chloride.
Brilliant.
Okay.
So this is, yeah, I would say this would be a way of finding it in a very indirect way, knowing all the other energy transformations, ionization, making it into a gas, etc., etc.
Yeah, the enthalpy of formation is one we can get by experiment. The one we can't get by experiment here is the lattice enthalpy. You're not going to easily turn gaseous ions into an ionic compound by experiment. So it's this one is really what the Born-Haber cycle is used to find, because it's the one we can't find via experiment.
Right, yeah, that's very smart, actually. Just using chemical energetics. Brilliant, sounds good, yeah, thanks for that, Paul.
Okay.
Look forward to doing another video with you. Yeah, bye for now.
Thanks, Hassel. Bye.